Let's do one last problem. This is, I normally wouldn't actually push it so much, but this one, the reason I'm doing this is just to illustrate an important fact. Although it's kind of rare to for this to be shown, but anyways, I think it's pretty insightful. Well, suppose say you have y prime equals, let's see, 2xy. So let's see, 2xy. Okay, um, e to the power x by y squared, divided by y squared. It's gonna be pretty big. It's gonna be pretty big. Plus y squared e to the power x minus 1. And I promise there's really something new to learn here. It's not just me doing hard problems just because. Okay, so actually we'd see that, given that we make the right decision, okay, and that's basically what I want to illustrate here. This is not that hard of a problem. It's not that hard a problem. So the thing is, what I'm trying to say is there's quite a few things to learn here. Okay, one thing is, if you see that expression, okay, obviously everything outside, everything should be, y prime. If you have, y prime here, first thing, it's really not separable. The second thing is, for it to be homogeneous, everything needs to be an expression of y by x or v. So we obviously need to make sure of that. Obviously the outsides we can see, if you divide both the numerator and denominator by x squared, okay, by x squared, we would actually get that. We could at least, I deal with these, kind of like coefficient or an algebraic terms first. So what we're gonna have here is, two, this x cancels out. So you have a v. You basically have a y by x. I'll just write, actually, yeah, I'll just write that as y by x for now. Okay. Multiplied by e to the power x by y squared. Okay, and etc. On the denominator you also have, this is squared, v squared. This is just 2. But anyways, the main thing I want to talk about here. Okay, actually, first thing, what we should see here, what I wanted to mention is, see here, see this, this is the first order differential equation, and in an exponential function you have something like x by y. Okay, or you could even have something like, y by x, and square. Basically, when this sort of an expression is in an exponential or trig function or something like that, where it's not really easy to bring this out or anything, or manipulate it or something like that, to break y and x up. Okay, an exception is, natural log, because, if you have natural log of y by x, you obviously be able to separate that, right? Natural log of y minus natural log of x. Okay, so that one's not counted. Natural log, or log, is not counted. Okay, but for functions like the exponential one, or the trig functions, sine, cosine, tangent, and all of that, so basically functions where, if you see in these functions y by x, and for these ones, it's not gonna be easy to manipulate this and to break this up like here, or to bring this out. It's really a dead giveaway, a very dead giveaway, that we are dealing with a first order homogeneous differential equation. So that's just something to take away here. So it's a very, I should really even write this out. This fact that we are seeing this expression right here, or this expression right here, all of these are actually the same. But anyways, or even if you saw something like, sine of y by x, or something like that, it's a very dead giveaway. It's a very dead giveaway that we are dealing with a first order homogeneous differential equation. All right. So if that's one thing, and the other, it's equally important, that I wanted to mention here, is that if you make that substitution, try to make the substitution v equals y by x. Obviously it would work. Okay, here, I already said that all of these, kind of coefficient or algebraic terms would be functions of v. Inside also, x by y squared, what is that? You have e to the power x by y, and that is squared. Well, x by y is 1 by v, so you have 1 by v squared, and that's basically gonna be 1 over v squared. Okay, so you could do that. At the end you'd have something like this. For the y prime expression, you're gonna have something like this. So let's see, v e to the power 1 by v squared plus, okay, so you have v squared 1 plus e to the power 1 by v squared plus 2 e to the power 1 by v squared. Okay, the thing is, this isn't easy to solve. This isn't easy to manipulate either. I'm not saying it's impossible. To be honest, you can try it out yourself. I myself did try it out and got really hairy. and I really wasn't motivated to do this. And the reason is because this exponential term right here, even though we were able to express this in terms of v, it's not really, it's, since it's e to the power 1 by v squared, it's actually really hard to deal with. Okay, and even in sine terms, if you have something like sine of 1 by v squared, okay, usually that's going to be hard to deal with. So you can try making this substitution, and then solving it this way. It's going to be pretty hairy, pretty messy, not recommended. So what you should actually do is, there's really this variation of the substitution that we're doing, okay, and it's really just the reverse one, okay. So what we need to what we need to see is that these kind of, like, you could say, stubborn functions, okay, what's inside them? It's not y by x, it's actually x by y, right? So why not actually make that substitution instead of saying v equals x by y? Why not make the substitution instead of saying v equals y by x, why not make the substitution u equals x by y? Okay, our initial purpose was just, it's not like v equals x by y is some sacred substitutions. Just because our right side was a function of the ratio of y and x, or basically x and y, okay, and then we made the substitution just to make things simpler, for the sole sake of sole purpose that this is the ratio, and we're just equating it with that. But we could make the reverse argument here. It's really the same argument here. So we find this more convenient to do, so we can just do that, no problem, okay. So for that, we just need to change things up a bit, okay. One thing is, obviously we don't have VO, so that substitution for the derivative is not really allowed. So if you have uh, u equals x by y, what you're gonna have for x, so x is gonna be equal to yu, okay, yu. And if you take the derivative of both sides with respect to y, not with respect to x here, derivative this, keep that one the same. So what you're gonna have is 1 multiplied by u, so basically u, plus, keep this the same, derivative this with respect to y, this is y du by dy. So now what we can do is actually put this in the original equation. Well, one thing is, we first need to this is the expression for y prime, okay. The expression for x prime, basically, or dx by dy, is just gonna be the opposite. So dx by dy, I shouldn't be saying opposite that colloquially. So anyways, it's gonna be the reverse, the reciprocal of this, okay. So one thing is, the main purpose that we use this a slightly different substitution, okay, but same nature, is that this thing, that e terms all over, that are all over here, okay, they are actually much simpler now. It's not going to be it's not going to be 1 by something. It's going to be, if we have x by y whole squared, it's basically, what's x by y? It's u. So you have u squared here. So same thing here. So you have, actually we were reverting this, right? We were reverting this. Anyways, my point stands, but the thing is, we need to revert this. We have y prime equals this. So we need to revert this. We need to, kind of take the reciprocal here. Okay. So what we are gonna have here is y squared. Actually, I'll factor that 1 plus e to the power. I'll already make the substitution here. We have u squared, 1 plus u squared, plus you have 2x squared, 2x squared, e to the power. So u squared divided by 2xy e to the power u squared. Okay, now it's really the same thing that we did before, just we now need to express terms as x by y in terms of x by instead of y by x. So what we are going to do is actually divide both the numerator and denominator by y squared, okay, by y squared. So this is going to go out, x squared by y squared, this x by y whole squared. What we're going to have here is 1 plus e to the power u, that squared, plus 2 multiplied by x by y whole squared. That's basically x by y is u, so that's u squared to the power this. So you have that, and then you have 2. This cancels out. You have x by y, so u e to the power u squared. And I think that you see this is much easier to manipulate. And one thing we should do, we should replace dx by dy by this expression right here. Then the one we got, u plus y du by dy, u plus y du by. So, and I forgot to mention this, but why is this gonna work? It's really again the same argument as before. Is if we do this, we are, given that it's homogeneous, we're gonna get, a differential equation with only two variables in it, specifically u and y. Okay, specifically u and y. So, and similarly as we proved, with v, this is also gonna be separable. This is equally also gonna be separable. So it's gonna be 1 plus e to the power u squared plus 2 u squared e to the shouldn't have, actually I should have written that there, so we u squared, yeah. So yeah, so now what can we do? We can subtract u. Okay, this looks too much like v. Yeah, we can subtract u here. Couple of ways to think about this. You can divide this by this, so you basically are gonna have a plus u here. Okay, plus u, so you're gonna, yeah, so you can actually cancel that with this one. Okay, now we can actually, well, obviously this is not totally cancelled here. The denominator is obviously going to remain. Okay, so anyways, now what we can do is actually separate the variables. We can actually separate the variables. Okay, so bring all the u terms here. Just take the reciprocal of this whole thing and multiply this here on the other side, the left side, and we just need to, yeah, so divide by y multiplied by dy. So on the left side, what we're going to have is the reciprocal of this large thing that we have on the right side right now. So 2u e to the power u squared 1 plus e to the power u squared, yeah, u squared, and this is going to be multiplied by du, and it's going to be equal to 1 by y dy. And I think you can see now, if you just notice one thing, it still might kind of appear a bit difficult, but it's really not, because see, this is the derivative of our denominator. This is the derivative of our denominator. And whether you'd like to use kind of like a formula, like you have some derivative divided by the original function. Obviously it's y here, but anyways, whether you'd like to use this formula where at the end you'd get natural log of absolute value of the function, basically the function at the bottom you have denominator, or you'd like to use u substitution. Well, it's already u, so it'd probably rather use w. Either way you'd like to do that, if we take the integral of both sides, okay, if you take the integral of both sides, either way you'd like to do this, so what you're gonna have on the left side is natural log of absolute value of this thing in the denominator that we have. So this original function, you could say, in the denominator. So yeah, okay, so this is what we have here, and on the other side what we have is natural log of, again, you're gonna have a constant here and all that stuff, so that's why I'm just gonna put a k here. So k multiplied by absolute value of y. Now we can take the e to the power on both sides, or the anti-log, you could say. So absolute value, actually we don't actually need an absolute value here. It's always going to be positive. This is always going to be positive. So since this can never be this can never be negative, so this is always going to be positive. So that's why we can just relieve that there. Not so much on this side. Y can still be negative. So let's see, k absolute value of y. Now all that we need to do is actually back substitute. What is u? U is basically x by y. Another thing, since we want y, we can actually divide both sides by k, but that's again just some constant. That's really the same thing as multiplying by some constant. So that's gonna be on the other hand, let's say it's capital K multiplied by 1 plus, we are reversing our substitution, so u equals x by y. This we need to be careful. It's not y by x, okay? It's x by y. Now, this is basically our solution. So you have y, the absolute value of y here. This is always going to be positive. This has the same sign always. The thing is, y is the absolute value really doesn't play any role here. Suppose if this were, this side were negative, okay? Actually, it's not possible, okay? It's not possible for it to be negative. Yeah, absolute value of something cannot be negative. So it can be either 0 or positive. Well, if it's already, greater than or equal to 0, to be honest, we don't really need the absolute value, right? So y itself is just equal to some constant k. It has to be a positive constant, okay? So k is kind of bounded. It has to be a positive constant multiplied by all that we have here. That this is the final and probably the most neat solution that you can get for this. So and actually, yeah, as you can see, this is an explicit function. Okay, it's y is not expressed directly or explicitly as a function of x. You have x by y here, but still it's probably the most aesthetic solution you could get here. But anyways, that's all that I needed to or had to cover in this video. I think we have gained mastery of sorts in solving these first order homogeneous differential equations. Okay, so it's all about, first thing is we need to confirm that whether it's a homogeneous equation or not, whether you can do it in a couple of ways. You can eyeball the equation and then say whether it's it or not. Or if that isn't enough, or you're not exactly convinced, not sure, okay, or if it's required of you to prove it manually or prove it rigorously, you can make that tx and ty substitution as we did here. Okay, and see the differential equation is unchanged, and then you can say that it's homogeneous, and then just make the substitution, put in the relevant expression for b or u, whatever you choose, and then you can solve it. Oh yeah, one last thing is, usually, especially when you have only algebraic or polynomial terms in your differential equation, in these homogeneous equations, it really usually doesn't matter whether you choose the u in u equals x by y or v equals y by x. Okay, so it really doesn't matter usually. Both of those are really have the same, both of those have the same length or complexity. It's just, as I said, if your that thing, x by y or y by x, whatever it is, that ratio, if it's in some function that's it's kind of stubborn, or it doesn't really let go easily. So whatever's inside it, you cannot manipulate or break that down or separate that easily. Okay, like this exponential function, or even like the trig functions. Okay, so for those, you'd really rather make the substitution according to what's in this function. Okay, according to what's inside these stubborn functions, you could say. Okay, so since we had actually, why am I highlighting this one? I should have highlighted this one. Since we have x by y, okay, you should definitely do the substitution of x by y, not y by x. Anyways, so that's all that I needed to explain here. So see you later, and study smart.